All right, so let's talk about different types of hypotheses. There is what is called a simple hypothesis and a composite hypothesis. A simple hypothesis means that theta can only take a single value. Okay, so it cannot take a range of values, or the underlying distribution of our observations is unique. Okay, in that case, the hypothesis is a simple hypothesis. In the composite hypothesis, the underlying distributions can take a class of distributions. Underlying data can take a family of distributions, okay, a range of distributions. Perhaps because there's another unknown parameter, okay, or theta itself can take a range of values. All right, so a good example is, of course, the signal present, signal absent problem that we have discussed before. Here, both the null and the alternative hypotheses are simple. If, on the other hand, theta, so in the second example, if theta takes a range of values, say between in the interval 0 to 1, then the null hypothesis is composite, but the alternative hypothesis is simple. All right. Now, there are also different types of tests. Okay, there is what is called a one-sided test, where theta takes a value, a single value, h sub 0. So our null hypothesis is simple. Alternative hypothesis, on the other hand, theta takes continuum of values. Okay, and in that case, of course, theta, the alternative hypothesis is composite. There's also two-sided tests. The null hypothesis is simple, theta takes value theta sub 0. Alternative hypothesis, on the other hand, theta can take any value but theta sub 0. Okay, so we'll see that in the context of Bayesian hypothesis testing, these differences between test types do not matter. We handle both simple tests, composite tests, any types of tests in the same manner. But in the context of frequentist approach, those are handled differently. Okay, so obviously simple tests is pretty straightforward to address. We'll see that we'll address this with Neumann-Pearson detection. But for composite tests, we need to go to a different type of test, what is called the uniform loss powerful test. All right, so here's an example. So say we want to detect a sinusoid embedded in noise, which is a typical problem in electrical engineering. So a sinusoid has a fundamental frequency f sub 0 and a phase phi. Let's assume we know the fundamental frequency, but the phase is not known. And let's assume we know the variance of noise. Then we can formulate the detection problem as signal absent, signal present. In other words, the measured signal is simply noise if there is no sinusoid. And if the sinusoid is present, then the measured signal is the sinusoid plus noise. So we see here that the null hypothesis is simple. Alternative hypothesis is composite because phi is unknown and it may take a range of values. Right, so we will use this concept of test functional or test function widely. We can define the goal of detection problem or hypothesis testing is to define a mapping T from our sample space to the set of hypotheses, because ultimately we have to make a choice between m different hypotheses. So we are looking for a mapping that is going to map our observations to the set of hypotheses. And this mapping is called the test functional, okay? And this is also our decision rule, of course. Okay, so when I say decision rule, I would mean the mapping from our observations to the set of hypotheses. Now, a decision rule is going to partition our observation space into decision regions. Okay, so given our decision rule or test function, we are going to define m different regions in our sample space for m different hypotheses. If x falls into a location such that x is mapped to the hypothesis h sub k, that is region r sub k. So for all the observations that are in region, let's say r sub k, are mapped to the hypothesis h sub k. Okay, so to visualize this, we can assume that we have a two-dimensional feature vector, and we have four different hypotheses, and we design a test functional and decompose our sample space into four distinct regions. Obviously, these regions are not overlapping, otherwise T would not be a mapping. Okay, so they are non-overlapping and there are boundaries between different regions. So to see that, suppose we make observations, and each observation is a Gaussian with mean theta and variance 1. We have IID observations, and we consider the test of theta being 0 or theta being 1. Okay, so a simple test function would be simply take all our observations and look at their mean value. Okay, so observations, we look at the sample mean, and if that sample mean is less than half, it's more likely that they are coming from a distribution, Gaussian distribution with mean 0. If, on the other hand, sample mean is larger than 1/2, then our observations are coming from a Gaussian distribution with mean 1. So we see that in this case, our test function or decision rule divides the sample space, which is an n-dimensional Euclidean space in this case, into two regions, and the boundary between these two regions is a hyperplane, which is defined by the sample mean, essentially. So that is the boundary is that the sum of the sample mean is 1/2. Okay, so that's going to define an n-dimensional hyperplane. All right, now to complete our decision or detector design, we also define what's called the thresholding rule. So once we have the test function, which maps our observations into a scalar quantity. Okay, so we have, this usually goes under the name discriminant function. Okay, so not test function, but discriminant function. So you have all your observations and you design a discriminant function which is going to give you a scalar quantity, a highly informative scalar quantity, most likely a sufficient statistic for theta. It's some kind of minimal sufficiency statistic, of course, on theta. And now you are going to design a threshold which will help you decide between the two threshold, the hypotheses. Okay, so if the output of your discriminant function is larger than that threshold, you're going to declare null hypothesis, otherwise alternative hypothesis. And of course, the threshold, along with the discriminant function, is going to define the decision regions in your sample space. Now, lastly, the error analysis. How do we really quantify the performance of our detection scheme? We will be using 4 different measures. The first one is the detection probability. So it's typically defined as, given that the true nature of the state was that the alternative hypothesis is true, and the probability of declaring H1 is called probability of detection. Okay, so, or to put it simply, the probability of declaring that the target is present when actually there is a target. Okay, misprobability, on the other hand, are also called false negative. All these terms are from radar literature. There is indeed a target out there, but we declare there is no target. And obviously this is the complement of probability of detection, which is equal to 1 minus the probability of detection. This is called misprobability, or in medical diagnostics it's called false negative. Okay, so you didn't detect the disease and it's a false negative. Now, thirdly, the false alarm probability. That is the probability of declaring that there is a target when there is actually none. Okay, so that's a false positive, or probability of declaring that the patient has a certain disease when actually the patient does not. Okay, and finally, now the rejection probability. That is probability that we declare there is no target when actually there is none. Okay, which is a complement of the false positive and equal to 1 minus the probability of false alarm. Now we see that the probability of detection, the design of a detector is a compromise between the probability of detection and probability of false alarm. So if you consider the problem of detecting a target out there, I can, irrespective of what data I observe, I can declare that there is a target out there. And with 100% probability of with 100% probability of detection, I will always detect the targets. So I will never miss a target. But on the other hand, I will also be doing 100% false positive. So I will be alarming all the time. On the other hand, irrespective of what data I observe, I can say that there is no target. Okay. In which case I will have no false alarm, but I'll have 0 probability of detection. So we'll see that there is designing a detector is a compromise between these 2 terms. And here is a graph showing you probability of false alarm and misdetection, the 2 errors. Okay, so the underlying distribution of X under the null hypothesis is F sub theta 0, and under the alternative hypothesis it's F sub theta 1. All right. Now, probability of false alarm is, and we have a threshold theta. Okay, so if x is larger than, threshold gamma. If x is larger than gamma, we declare alternative hypothesis, and if x is less than gamma, we declare null hypothesis. So probability of false alarm in this case is that our observation x is larger than gamma, but it actually comes from the underlying distribution f sub theta 0. Now, probability of misdetection, on the other hand, is that we observe x and that x is less than gamma, and we declare null hypotheses, but actually it comes from the underlying distribution f sub theta 1. All right, so another example that we have here is from radar. We have a transmitter and a receiver and a target out there, potentially a target. So we transmit a signal S of t, and we receive a signal S of t minus tau. That is a delayed version of the transmitted signal. Here the delay tau has to do with the travel time of the signal that we are transmitting. Now, if there is a target out there, the transmitted signal is going to be delayed and scattered from the target and be received by the receiver. And then we will have some added ambient noise on top of the received signal. If, on the other hand, there is no target out there, the signal that we transmit will propagate indefinitely, and what we will be observing at the receiver would simply be the ambient noise. Okay, right? So we can, of course, alternatively formulate this problem as null hypothesis being theta equal to 0 and theta is equal to 1. If we rewrite the signal x of t as theta times s minus t minus tau plus the noise. Okay. Now you'll see later in class that an optimal detector in the presence of Gaussian noise is the filtered version of the received signal. So we will get the received signal for a period of time, say cap t, and then we will pass it through a convolution filter, some kind of optimal filter, and we will subject the output of this filter at time cap t to a threshold, and that threshold in this case is nu. So if the output of our filter at time cap t is larger than nu, we will declare alternative hypothesis, otherwise null hypothesis. Okay. So of course, the output of our filter at time cap t is y, some scalar quantity y, and if y is larger than nu, when there is no signal, then we would be making a false alarm. If, on the other hand, there is signal, but the output of our filter y is less than nu, then that will be a misdetection, right? And we can compute, given our filter and given the underlying probabilities, etc., we can compute the probability of y under each hypothesis. So under null hypothesis, probability of y is f sub theta sub 0, and under the alternative hypothesis, its probability is f sub theta sub 1. Okay, so probability of false alarm would be that the underlying distribution is actually has the parameter theta sub 0, but y is larger than nu. So that would be the integration of this probability when y is larger than nu. Misdetection, on the other hand, means that there is target, so the parameter is actually theta sub 1, and that but y is less than nu, so that would be the integration of the probability with parameter theta sub 1 when y is less than nu. Okay, all right. So of course the question in detection theory is that is there an optimal way of designing a discriminant function that is going to take all our observations and map it to a single scalar quantity, and also an optimal threshold, so that we have some kind of optimal way of trading off between probability of detection and probability of false alarm. Okay, and also, can we optimize this filter? Can we optimize the threshold, etc.? Now, we will cover two separate approaches, a Bayesian approach and a frequentist approach in designing a discriminant functional, as well as a threshold.